The only way mankind will exist in the future is through the mastery of controlled nuclear fusion. But fusion cannot be understood by enumerating its benefits or by calculating its electrical potential, although it is immense. The new quality of human civilization it will allow can only be adequately understood by looking at it in the long-term context of human development, from the physical world of the Stone Age to the chemical world of the Bronze and Electrical Ages to the nuclear world that we have only just ventured into. By contrasting these stages of physical, chemical, and nuclear, we can understand the profound importance of developing a fusion platform, and specifically one powered by the rare isotope helium-3, found naturally on the Moon, but not on Earth. We'll start by going back in time a few thousand years. "10,000 years before the present, in the Stone Age, our tools and technologies were material, physical. Many tools were made from rocks, which might be chipped into better shapes, such as for sharpening, and other materials used for construction and tools were those found around us or made from them, such as fiber, wood, bone, shells, mud, and stone. If someone considered what a rock was made out of, the answer would be smaller rocks, and wood was made of wood. The characteristics of objects that were of value, besides food, were what we would call material or physical ones, such as strength, hardness, flexibility, durability, heaviness, size, shape, temperature, and so on. The changes we were able to cause were in large part physical reshaping and cutting and grinding, as well as movement. The simple machines of antiquity, the lever, the screw, the wedge, the pulley, and so on, these are physical machines, which could transform one kind of motion into another kind. For example, lifting a weight could be made easier by using a system of pulleys. More rope is pulled, with less effort, to lift a heavy weight a shorter distance. Or one mass could be used to lift another by using a lever. This table includes some characteristics of the physical world, the kinds of machines we had created, the characteristics of materials that we'd be thinking about, and the kinds of changes that we could bring about. Not included in this table is the application of fire, the use of which absolutely separated the human species as a creative species from all other forms of life. The first evidence for the use of fire goes back hundreds of thousands, or perhaps 1,000,000 or more years. With fire, man could cook new foods to make them edible and safer, harden rocks to make for sharper edges, fire clay, increase the flexibility of wood by boiling, treat textiles to create fabrics. We could see and protect ourselves at night. We could clear land. We could bake. After wood fire, the first change in our power over nature that was of a truly different physical type was seen in the birth of the Bronze Age. The Bronze Age, like the later Iron Age, took its name from advancements in making metals. Bronze is a combination of copper and tin, which requires a new kind of power over nature to create, and the resulting material, bronze, is stronger and more durable than either copper or tin. This is malachite. It's a blue-green rock, and it was the primary source of copper in the Bronze Age. As a rock, despite its unusual color, it's not so different physically from other stones. It's not remarkable by its hardness, its weight, its durability, its ease in chipping apart to make sharp edges. Yet, when a new kind of fire is applied to it, something amazing happens. This new type of fire is that of charcoal. Charcoal is made from wood by partially burning it without air, such as slowly burning it under a pile of earth, as you see here. The resulting charcoal burns both hotter and cleaner than a wood fire, allowing for more convenient cooking than using wood, which creates a ton of smoke. A charcoal fire has the ability to cook malachite and turn this rock into a metal. Let's look at how modern-day researchers have recreated the process. After grinding up the malachite with a stone, they dig a pit, start a fire in it, add charcoal, add the ground malachite, more charcoal, and a top, and blow air into it with a bellows to keep the fire going. After some hours, the process is complete, the pit is reopened, the malachite has disappeared, and copper metal has been formed. This is an astonishing change, absolutely unlike any of the physical changes created before, and far more dramatic than the change of baking bread or of cooking meat. The very nature and material of the rock has changed in an almost miraculous way. It's hard to imagine things that are more different than a rock versus a metal. Metallurgy was the beginning, the first example of what were later called chemical changes. With the development of modern chemistry by Antoine Lavoisier and Dmitri Mendeleev, among others, the answer to the question of what is a rock made of was totally different. No longer was a rock made out of rock. Now the chemical elements, the smallest pieces into which the rock could be broken, including by these new kinds of processes, these elements were being worked out. A rock was now made of silicon and oxygen, in the case of this rock, or copper and oxygen, in the case of this malachite. And these component parts, oxygen, silicon, copper, they had absolutely none of the physical properties used to describe the physical materials they formed. For example, graphite, coal, and diamond, they're very different in their hardness, their color, their density, in almost every imaginable way. Yet these substances are all made entirely of the chemical element carbon. So carbon doesn't have a color. Carbon doesn't have a density. Carbon doesn't have a hardness. What carbon has is a susceptibility of entering into particular compounds with itself and other elements, making materials that do have physical properties. Yet the properties specific to carbon itself are chemical properties, not physical ones. They relate to the kinds of compounds it forms, the ease with which it does so, what ratios it combines with other elements in, and so on. The first chemical machine was metallurgy. The work of transforming rocks into metal was totally different than what could be done with physical machines, with cutting, grinding, pulling, scraping, banging, heating. None of that makes copper. The charcoal fire was pulling the oxygen away from the metal in the rock, in effect undoing the process of rusting, which is the chemical combination of a metal with oxygen. We saw this with the creation of copper from malachite. It wasn't just the heat of the charcoal fire, it's the chemical characteristic of it. Here you see a form of processed iron called taconite, which looks like balls of rust, which is essentially what it is. When it is smelted into iron, it is, in effect, unrusted chemically, by removing the oxygen. Around 1700, a powerful new chemical machine was developed and built, the steam engine, which used the potential of coal to change chemically, to burn, in order to produce motion. And now the power of a lump of coal was much greater than its ability to weigh down on a lever or a pulley. It could be burned to heat water, to produce steam, to push on pistons, as in a steam locomotive. Let's compare the physical versus the chemical power of a lump of coal. In order to get the same energy as burning a given amount of coal, you need to have 100,000 to 1,000,000 times as much water flowing through a hydroelectric dam, depending on the height of the dam. This means that the coal is nearly 1,000,000 times more powerful when it's burned chemically than its weight is were it to be used physically. This is the astonishing power, the astonishing energetic power of chemical machines. A whole new vocabulary now exists. Some of these new chemical attributes include valence, enthalpy, and atomic mass. These terms are likely unfamiliar. They relate to the ability of elements to combine, and in what ratios, valence. The heat released or consumed in such chemical changes, enthalpy, and the characteristic mass associated with a certain quantity of an element, determined by how it interacts with other elements. That's the atomic mass. This was a whole new domain of characteristics, and understanding it allowed us to create and understand a whole new domain of changes, including everything from soap to camera film, from cement to gunpowder, superglue, antifreeze, petroleum, plastics, new alloys, tougher steels. Recombining elements could create materials with totally different physical properties than previous compounds the elements had entered into. One particularly dramatic change was the chemical development of nitrogen fertilizers, which are responsible for the lives of a significant portion of the people currently living on this planet. That one discovery, that one innovation, very directly changed the potential global population of our species. This whole world of chemical characteristics, processes, and changes, it required a new vocabulary, and it represented a higher level of power than the purely physical changes of the past, of the Stone Age. To get into the next form of action, nuclear, we'll talk a bit about atoms, which were a contentious development in the field of chemistry. Elements, and atoms in particular, were understood as the fundamental components of matter. Their combinations might change, but the constituent elements and atoms did not themselves change. Take this wood fire, for example. Carbon in the wood combines with oxygen in the air in the burning process to form carbon dioxide gas. The carbon that was in the solid wood is still carbon when it's in the carbon dioxide gas. Well, wood is not a gas, but carbon itself can be in a solid or a gas. Carbon in one compound is still carbon when in another compound, and no techniques had ever been found that could change one element into another, even though alchemists had been trying for a long time to turn lead, for example, into gold. Atoms themselves are considered as a heavy nucleus containing positive protons and neutral neutrons, with a swarm or cloud of negative electrons swirling around it. Chemical reactions and changes are considered to be related to the interactions of these electron clouds around atoms, not the nucleus. Yet the nucleus determined what element the atom was. Understanding of the nucleus moved forward with, you guessed it, nuclear science. You know, we sometimes forget today that the word nuclear means pertaining to the nucleus. You yourself are very nuclear. There are several thousand trillion trillion atoms in your body, and each one with radiation, truly a fascinating subject, led to the hypothesis that the nuclei of atoms were themselves sometimes changing and emitting various sorts of radiations as they did so. This was a new kind of change. Physical changes to a rock still make pieces of rock, and chemical changes to a rock may pull apart the elements, but they don't change them. Remember, the copper was already in the malachite. But now, the nuclei, the type of atom, the element itself, was actually changing. Parts of the nucleus were energetically flying off. The most common changes were the nucleus emitting 2 protons and 2 neutrons, together called an alpha particle, or a single electron, a beta particle, or a high-energy light-like ray, called a gamma emission. These names come from alpha, beta, and gamma being the first 3 letters of the Greek alphabet. So the amount of energy that could be given off was astonishing. It overthrew the laws of physics. To give an example, a given mass of radium, which is a very radioactive element, it emits as much energy over time as 500,000 times its mass in TNT. This is a tremendous amount of energy. Remember that the coal has hundreds of thousands times more energy when burned chemically than when simply weighing down physically. And now a nuclear process is about 1,000,000 times more powerful than a chemical one. So overall, there's about 1 trillion times more power in nuclear processes than in physical ones. But this radiation energy is typically released very slowly. It would take 1,600 years for a piece of radium to release half its energy. That's its half-life. This would mean that if you wanted to go off the grid and power your house or apartment with radium, you would need several hundred pounds of radiating radium to make enough energy. Radiation is quite weak, and it's totally unsuitable as a large-scale power source, although radiation energy does power the Curiosity rover up on Mars. But radiation, it's not energetic, it's not very powerful, and it's certainly not how nuclear power plants work. They're not based on radiation. If they were, they'd hardly make any electricity at all. There's another kind of nuclear change we need to know about to understand this. It was discovered that some nuclei, instead of only emitting these puny radiations, would also sometimes crack and split in half, creating 2 new atoms of varying types, along with several neutrons and a tremendous amount of power. This breaking apart of a nucleus is called fission, and it happens spontaneously in some kinds of nuclei. But what made nuclear power possible was the discovery that, unlike normal radiation, which just occurs on its own in certain nuclei, fissions could actually be caused when the nucleus was stimulated by having a neutron smash into it. By arranging enough of these fissile, that's a word that means capable of stimulated fission, by having enough of these fissile nuclei gathered together, a chain reaction process could be made where one fission would cause other fissions with the neutrons it created, which would in turn make more fissions, and so on and so on. This could release a great deal of energy very quickly, and it could be useful for power, unlike natural radiation, which basically makes rocks get warm. This power of fission is what happens inside current nuclear power plants. And except for a few very unusual geological formations, this fission never occurs in nature. It is a specifically human-created form of fire. It is only made by us. So now, with the nuclear world, we have a whole new vocabulary to introduce. Our nuclear terminology includes cross-section, how easy it is to cause a nucleus to react with another particle, decay type, alpha, beta, or gamma, half-life, radioactive nuclei now have lives because they change on their own. And isotope, which means same place, and names different varieties of the same element. Isotopes are in the same place on the periodic table, but they aren't exactly the same substance. For example, the uranium that we mine here on Earth is actually a combination of two different kinds of uranium, called uranium-235, or U-235, and uranium-238, U-238, which are chemically indistinct, and they're both called uranium by a normal chemist. Those isotope numbers, 235 and 238, are the total number of protons and neutrons in the nucleus combined. All uranium has 92 protons, which is what makes it uranium, just like having 8 protons would make it oxygen. Uranium-235 has 143 neutrons, along with those 92 protons, making a total of 235, which is why it's called uranium-235. U-238 has 3 more. It has 146 neutrons, which, with the 92 protons, totals 238. This difference of 3 neutrons between 143 and 146 doesn't seem to mean much chemically, unlike a difference in protons, which would make a different chemical element. A different number of neutrons makes a different nuclear isotope. But there is a major difference here. Uranium-235 is fissile, meaning it will fission apart, split apart, when struck by a neutron, and uranium-238 is not. That's why uranium enrichment is performed, to concentrate the uranium-235 needed for a power plant. We still don't know why some isotopes undergo fission and others don't, or what the configuration or shape or nature of the nucleus is with these different numbers of nucleons. Examples of nuclear machines today include nuclear power plants, nuclear explosive devices, which, fine-tuned, could see application in excavation projects, medical scans that use special isotopes, or food irradiation to prevent disease and food waste and starvation from food spoilage. The power of a rock of uranium can do much, much more than a physical rock might weigh down on a lever, or a chemical rock, coal, might be burned to produce heat, although you can burn uranium if you want to. But this nuclear uranium can undergo a nuclear change and release 1,000,000 times more power than if you burned it chemically, and 1,000,000,000,000 times more than if it were used physically as a weight to push down on a grandfather clock to keep it running, for example. And that's only the part of its use that can be compared to lower levels of power, like making electricity or weighing things down. I mean, you can't perform a medical scan of your thyroid gland or look at broken bones in your arm with any number of rocks connected to pulleys, levers, corkscrews, or with a gigantic pile of charcoal, or with a bunch of chemicals. It's just a different kind of process. But today's nuclear is not the end of the story. We need to necessary technology and power platform of the future. Unlike fission, which is the breaking apart of large nuclei, like uranium, fusion is the combining or joining, or fusing, of small nuclei. One example fusion reaction, the one that's most commonly studied today, is that between deuterium and tritium. Deuterium is an isotope of hydrogen, and all hydrogen nuclei have 1 proton, shown here in red. However, unlike most hydrogen, it also has a neutron, which we see here in blue. Since deuterium has 2 nucleons, it has the name deuterium from deutero, which means 2, like in duo or duet. Both normal hydrogen or deuterium can form water by combining with oxygen. They're chemically nearly identical. Tritium, like tricycle, which has 3 wheels, is also a kind of hydrogen. It's an isotope of hydrogen, and it has a total of 3 nucleons, 1 proton, because it's hydrogen, and 2 neutrons, making a total of 3. Tritium. When deuterium and tritium combine nuclearly, which is difficult to make happen, and we still don't fully understand the process, there are a total of 2 protons and 3 neutrons, which results in a helium nucleus, 2 protons and 2 neutrons, and 1 extra neutron. Let's watch that again and count the nucleons. This is a nuclear characteristic. The chemical combination of 2 hydrogen atoms, including deuterium or tritium, just makes hydrogen gas and a tiny bit of heat. But the nuclear fusion can produce a huge amount of power, 1,000,000 times more. The magnitude of power made possible by fusion could eliminate the problem of droughts by large-scale desalination. It will eliminate resource shortages by making ore processing tremendously easier, allowing even low-quality mineral deposits to be mined. And it holds the potential to eliminate any shortages of power for living, commerce, industry, or agriculture. Plus, the fuel's easy to come by. Deuterium can be found in normal water, and tritium can be created from easy-to-find materials. But there is a problem with this planned deuterium-tritium fusion. Similar to the way you can't use a magnet to pick up a piece of plastic or paper, the neutrons made by deuterium-tritium fusion, those blue neutrons can't be controlled by a magnetic or electric field like those used in most fusion experiments. Here you see protons and neutrons, and only the protons are affected by the magnetic field. Since the neutrons cannot be directed, they just shoot off uncontrollably in whatever direction, and they hit the walls of the fusion device, making it get hot. Now, and this is embarrassing for these fusion scientists, but the current embarrassing plans for fusion power call for using that heat to boil water or heat a gas to spin a turbine, just like the steam power plants of the 1800s. A much more powerful and useful reaction is between helium-3 and deuterium. Helium-3 has 2 protons, which makes it helium, and unlike normal helium, which is helium-4, this helium-3 has only 1 neutron rather than 2. So 2 protons and 1 neutron, helium-3. Let's look at a fusion between helium-3 and deuterium. If we count up our nucleons, we see that combining helium-3 with deuterium gives a total of 3 protons and 2 neutrons, producing helium-4, 2 protons, 2 neutrons, and an extra proton. Unlike the uncontrollable neutrons we saw earlier, these products are both charged, allowing something very special to take place. The entire reaction, including the products, can be controlled by magnetism and electric fields, allowing us to go beyond the benefits of deuterium-tritium fusion. We could divert the products to directly make electricity without spinning turbines or heating anything. We could create proton beams for transmutation. We could use it to create directed space rocket fusion thrust, which we will need to have an adequate defense against asteroids, and many other properties that we have yet to discover. Helium-3 will allow us to finally stop using heat, a physical property, for power, and to truly work on the nuclear and electrical level. And acquiring helium-3 requires making a very big leap. one beyond our planet, in fact. There's very little helium-3 here on Earth, maybe a couple 100 pounds. But there are millions of tons on the moon. China has expressed its intention to develop this resource, and the world should join this outlook. To review, we've discussed different levels of activity and understanding: physical, chemical, nuclear, and fusion. The tables you see show some of the language used for each level of understanding, which shows up in the questions of what is matter made of? What changes can we create? What technologies are at our disposal? We've seen that as we move smaller on the scale of our action, from physical stone tools to chemical reactions to tiny nuclear changes, we've moved much larger on the scale of our power, from physical machines based on motion to chemical ones based on combustion and transforming materials, to nuclear ones of incredible power and new capabilities. And in this nuclear world, 1 trillion times more powerfully, energetically, we've seen why it's helium-3 fusion, which will be the first kind of fire not based on heat, as we move more fully beyond the world of physical characteristics. Fusion is not an option. It is not a power source, and it must not be delayed. It is the natural next stage of human evolution, and is being pursued by leading BRICS nations, Brazil, Russia, India, China, and South Africa, even while it's being shut down and starved of funding in the US. If we are to join the new economic and political paradigm now blossoming around the world, we must embrace the creative identity of man and make fusion, with moon-based fuel, a goal that we are unwilling to postpone, one we intend to win.